Morning, guys. Today we're going to talk about force, mass, and acceleration and how they're related. The other day, we've been talking about how we calculate net force on an object, knowing all of the forces that are acting on an object. But today we're going to talk more conceptually about how the force that an object can apply is based on its mass and its acceleration. Okay. Um, So as we move forward, there is some math involved in this. There's a formula, F equals M times A. But again, we want to talk specifically here about the conceptual part of what all of this means. And honestly, you've known about this stuff since you were very, very young. You just didn't know about the math or the vocabulary that we apply to certain things. So when you were young and sitting down in the living room and pushing your toy cars around or pushing a chair around or pushing anything around in your house, it didn't take you very long to learn that the bigger an object was, the harder you had to push to move it. So if you had a little tiny Matchbox car, Hot Wheels car, you didn't have to push that one very hard to get it to go down the hallway fast. But if you had a bigger car, then you had to push that a lot harder in order to get it to go as fast. Okay. So again, this is not something that you don't already know. All we're doing here is applying some vocabulary terms to the actions and the characteristics of objects, and we're also including the math involved in it. So Isaac Newton was the man that kind of came up with his second law of motion that we'll talk more specifically about later on. And basically, what that law says is that the force that an object applies is equal to its mass multiplied by its acceleration. Okay? So, mass, and there's another word, a new word is inertia. Inertia is the tendency of an object to not want to move. And inertia is related to an object's mass. The heavier something is, the harder it is to get it to move. Okay, so that's what inertia means. Inertia, inertia. The bigger an object is, the harder it is to get it to change what it's doing. If it's sitting still, it's hard to get it accelerated. If it's already moving, it's harder to stop it. So again, imagine standing out in the road and somebody skateboarding towards you, and you standing in front of them trying to stop them versus you standing in the middle of a road trying to stop a car or an 18-wheeler. So the more massive an object is, the harder it is to change its motion. So the mathematical formula that we'll talk about more in class is F is equal to M times A, where F is equal to force in newtons, mass is equal to, of course, the object's mass in kilograms, and A is equal to the object's acceleration in meters per second per second. So again, objects with more mass are more difficult to accelerate. And remember, acceleration is just any change in motion. So whether an object is sitting still or whether an object is moving, if we want to change its motion, then we are trying to accelerate it. So you can see here in the picture, the large rock here, much more difficult to move than the small rock here. And that's simply because of the mass or inertia of this rock versus the mass or inertia of that rock. So if we apply the same force to two objects with different masses, the one with the smallest mass is going to accelerate more. Again, common sense. If we have a marshmallow and we push it with some force, it's going to go far. But if we use the same force on a car, that car may not even move. The force may not even be big enough to get that car to accelerate. So again, the larger the mass, the more force is required to accelerate the object. Okay, so if we use the same force on different masses, the accelerations will be different. And again, we will learn how to calculate these things mathematically. The more mass means less acceleration unless a larger force is applied. So weightlifters know that when they put more and more plates on the bar, they're going to have to apply more and more force in order to get the bar to move from the floor to above their head. And that would be the acceleration of moving the bar from the floor to above their head. So here again, we have similar forces, small mass, large acceleration. Same force, large mass, small acceleration. Now we're using different forces, okay? So if we use a small force on a small mass, we can get an acceleration. But if we get a larger mass, we have to apply a larger force to get this acceleration to be the same. So if we want a baseball to accelerate at 10 meters per second squared, we have to apply a certain force. But if we want a bowling ball to accelerate at the same speed, same acceleration, 10 meters per second squared, we know we're going to have to push it with a larger force. So if we look at these two images here, we've got a sled dog pulling with an acceleration, or he's accelerating this rock at 2 meters per second squared. And the mass of this rock is 50 kilograms. So if we were calculating the force here, force is equal to mass times acceleration. The force here would be 100 newtons. So if we look over here, and if we take the mass of the van at 2,000 kilograms, multiplied times its acceleration, 0.05 meters per second squared, the force here is 100 newtons. So these forces are the same. So this dog is applying 100 newtons of force. This person is applying 100 newtons of force. But notice that because this van has a much larger mass than the mass of the rock, look at the small acceleration versus the acceleration that the sled dog produced. So again, the force being applied is in to the left, and the force here is being applied to the right. Direction of forces is always important. And will the rock and the van accelerate at the same rate? Well, of course not. Okay, the rock is accelerating at 2 meters per second squared, and the van is accelerating at 0.05 meters per second squared. Okay, so again, smaller mass, same force, higher acceleration. Okay, so hopefully just conceptually you get the idea of what I'm talking about. And now what we need to focus on in class is the mathematics behind this, as well as the concept, but also the mathematics and how we manipulate the formula F equals m times a in order to calculate either force, mass, or acceleration.